Hi, I'm Jen from Calc Workshop, and in this video we're going to learn about the most important technique in all of linear algebra, row reduction. So either the form of REF, or row echelon form, or reduced row echelon form, or REF. Both of these techniques are pivotal to your success in linear algebra. We're going to walk through a bunch of examples to make sure that you are successful in understanding this important concept. So check it out. All right, so let's look at the two forms of row reduction. The first one is called row echelon form. Some people refer to it as just echelon form, and others refer to it as Gauss elimination, since Gauss was the first to have actually come up with this idea. We abbreviate and say row echelon form is REF, which is referred to as row echelon form reffing Gauss elimination. Here's the idea. We're going to take a system, and we know we like the identity matrix. That's our main guy that we like, because ones and zeros are the easiest. What we want to do is to, using techniques that we're going to talk about in a second, is to reduce our matrix down so that we get ones along the main diagonal. If you can see that, ones going along the main diagonal, and if you see in the lower triangle, we're creating this lower triangle of all zeros. So again, the objective is to create an upper triangle of just numbers, and the lower triangle has all zeros with ones along the main diagonal. That is our objective. So what we're doing is we're taking a system, we're reducing it down so that we get ones down the main diagonal, zeros in the lower triangle. Now this is a square matrix, meaning we have 3 rows, 3 columns. So we know we're going to get a main diagonal. If you look here, it's not a square matrix. We have 4 rows and only 3 columns. This is a 4 by 3 matrix, so there really isn't a main diagonal to speak of. We can kind of tell it's got that diagonal feel, but it's not a nice cut symmetry that we can see in the first one, and that's okay. We're still going to try our best to get this main diagonal, if we can, kind of fudge it and say, okay, I know it's not square, I know I don't have a main diagonal going all the way down, but again, what I'm looking for is to get ones coming down diagonally, zeros in the lower triangle. Here's the big key. So we know that we want to get this lower triangle of zeros. For REF, here's what's got to happen. You get your ones, and everything below the 1 must be a 0. Everything below the 1 in each column must be a 0. So that is the main objective for REF. Now, what are these little asterisks? These asterisks represent any number we want them to be. We don't really care, because what we'll be able to do is do back substitution to find our answer, and we've seen how to do substitution. We've been doing it since Algebra 1. So the asterisks represent any number. What we want to do is get ones along a diagonal, zeros below any of the ones. That's for REF, row echelon form, or Gauss elimination. Now, why don't we like this one as much as the second one? Because at the end of completing this task, we're going to have to use the substitution method. And how many of us jumped at the chance to use the substitution method in Algebra 1? Not many of us. So we would have to substitute back in our numbers to simplify an equation, then substitute again to simplify another equation. It's not really helpful, and we don't like doing it. So what would be better? Well, not just getting zeros below the ones, let's get zeros above the ones as well. That way we don't have to back substitute. So that's the idea behind the second form of row operations, which is reduced row echelon form, which is REF. We refer to this also as Gauss-Jordan elimination, because Mr. Jordan came in after Mr. Gauss and said, hey, let's clean this up even better. So it depends on also your textbook and also your professor who's going to want to say which form, but we have REF and RREF. So we're going to ref or we're going to ref. So we're going to ref this guy, but we're going to row reduce it even greater. So again, if you look at the first example, what you're seeing is we still want to get the ones down the main diagonal just like we saw here. But the difference with this is that we just love zeros because zeros are easy. So we're going to get the ones down the main diagonal, but notice we have this lower triangle of zeros and we have the upper triangle of zeros. That's beautiful. That means we never have to back substitute. We're done, we're simplified, we're happy. So again, what we see here is that we do have a main diagonal here because we have a square matrix, which is nice. We get ones in a column. Anything above and below has to be a zero, which we see here. Well, look at this matrix. This is definitely not a square matrix. This is out of control, a lot of variables, a lot of equations. So what do we see here? Well, we don't have a main diagonal. There's no way for us to kind of slice that. But we can kind of tell that it is kind of making a diagonal kind of shape to it, which is what we're trying to do. We're trying to eliminate to the point where we're going to get that diagonal feel going down. But what's important is this. Everywhere we see a 1, so if you see this 1 right here, everything above and below it must be a 0. Well, there's nothing above it, but everything below has to be a 0. Look at the next column. Do you see a 1? I don't see a 1. So I couldn't care less what's in this column. But here, I see a 1 in the third column. If I see a 1 in the third column, that means everything else in that column must be a 0. Well, everything above and below are zeros. We did a good job. Look at the next column. In the fourth column, I see a 1. Everything above and below must be a 0, and it is. Look at this fifth column. I don't see a 1 at all. So it doesn't really matter that we've got zeros and random asterisks represent numbers. As long as it doesn't have a 1, I don't really care, and we've done our job and we've row reduced. Now let's look at this next column. In column number 6, what we see is we have a 1, which means everything in that column above and below it must be a 0, which is exactly what we see. In our 7th column, we see a 1, and everything else in the column is a 0. Our last column doesn't have a 1, so we don't really care. So that is the idea behind reduced row echelon form, or RREF. So over there, everything below had to be 0. For REF, for our REF, everything above and below must be a 0. So there's the big key. Everything above and below a 1 must be a 0. That's critical. So REF, everything below the 1 has to be a 0. In our REF, everything above and below the 1 has to be a 0. We still want to see if we can form that triangle going down, but we're not going to be always successful to do that. We know the overall goal is to get the identity because he's the easiest, but we're going to maybe have to kind of fudge that diagonal as we go. But again, if we can get 1s and 0s everywhere, we are on the right track. Now, what is also really important is to know what these 1s actually mean. They have a name. We don't just go around saying, hey, get your 1s, get your 1s. They actually are so important, they are pivotal to our answer, they actually get a name. So what I'm going to do next, I'm going to put a matrix up, and I'm going to show you its equivalent matrix in row reduced echelon form. And we're going to talk about what these numbers, these 1s and 0s really mean. All right, so we have this system. And what we've done is we've put it into an augmented matrix. And then what we're going to see is after we've completed all the row reduction techniques that we're going to learn, that equivalent values turns into this matrix, which is this simplified system. So we have this equivalent system to this one. So these two systems are equivalent to each other. This one looks a lot nicer than that one. It's because we've performed all of our row operations to the best of our ability. So we, in essence, have simplified our problems significantly. More importantly, we're going to see that we've got these 1s and 0s, and everybody loves 1s and 0s because they're so much easier for us to figure out. So what do we know? This matrix is more simplified than that matrix. And what we're seeing is that we've got these 1s and 0s. So what are these things called? Well, this one and this one and this one. We don't call them 1s, we call them pivots. The reason why is because they are pivotal to us getting the right answer. So these values right here, these ones that we see, are called pivots. They are also called basics or basic variables, but you're going to see pivot more often than you're going to see basic. They are basic values, they are pivot values, they are pivotal to our answer. Now, what does that mean? So how many do we have? We've got 3, but wait a minute, we had more than 3 variables. We had x sub 1, x sub 2, x sub 3, x sub 4, and then we had the equals, and then we had the b's, the solutions. Well, that means we have a pivot in the x1 column, we have a pivot in the x2 column, and we have a pivot in the x4 column. Why don't we have a pivot in the x3? Well, what we see here is that we don't see a 1. If we see a 1, everybody else in that column must go to 0. We don't have a 1, so we don't need to see that everything goes away. So that means that this guy right here is what we consider a free variable. He is free to be whatever we want him to be. So what we're seeing here in a more general form is that this little guy is a free variable. So I'm going to try to put that in a different color so we can see it. So we have free variables, which in essence say they are free to be whatever we want. They are free to be whatever we choose. So the pivots, the basic variables, they're going to give you an exact value based off of the mechanics and the chemical makeup of these equations. The free variables, well, if we know he's free, well, I like the value of 1, let's plug him in. But if you like the value of 2, you plug that one in, changes the question just a bit, it's a scalar multiple. So what's interesting is that the 1s are no longer referred to as 1s, they're referred to as pivots. And the columns that they appear in are referred to as pivot columns. Now the pivot columns always go back to the original matrix. So the pivots are found in the reduced row reduction matrix. The pivot columns go back to the original. So we saw the pivot columns appeared in column 1, column 2, and column 4. These are the pivot columns. So the pivots are found after row reduction. Once you've done the row reduction, you found your 1s, those are your pivots. Once you found your pivots, then you can say, oh, in the original matrix, these were the pivot columns. So that's how we kind of relate the two. So what's interesting though too, is that we can then talk about, well, which variables are basic, are free, or excuse me, basic or pivots, and which ones are free. If we can't see it here, it's obvious that x1, x2, and x4 are the pivots, and x3 doesn't have a 1 in it, so he's got to be the free variable. We can see it even better up here. What we're seeing, if I rewrite this, we can then say, if I kind of put this down here, if I move everybody over to the right-hand side and solve, what we're seeing is that x sub 1 equals 5 plus 3x sub 3. I'm just moving the 3x sub 3 to the other side. We see that x sub 2 equals, and I'm going to bring the other guy over to solve for x sub 2, is negative 3 minus 2x sub 3. Well, I see that x sub 4 equals 0 in the bottom row wiped out and 0 equals 0 all the time. But what does x sub 3 equal? We didn't have a pivot. That means x sub 3 is itself. It can be anything we want it to be. So our pivots, so once again, our pivots for this specific question are x sub 1, x sub 2, and x sub 4. Our freeze is x sub 3. So these are pivot positions. Our pivot columns go back to the original matrix. So now that we know what these things are called, what are we going to do? How are we going to get from this guy to that guy? Let's talk about the row reduction algorithm. All right, so here are the steps that we're going to use to perform row operations. There's only 3. So the row operation rules, here we go. We can replace. What does it mean to replace? We can add two rows together. Now, what's really important is that you're only allowed to add. You can't subtract. We can add a negative, but we cannot subtract because subtraction is not commutative, whereas addition is. So again, if we need to put a negative in there, we're going to add a negative value. But again, we can replace by adding two rows. We can interchange. We can switch two rows. So we can switch two rows, we can interchange them, saying, well, why did that equation come up top? Why don't we switch it? Because we can. We can scale. We can multiply any row by a specific number. We can multiply by a positive, a negative, a fraction, whatever we need it to be, to either make it bigger or smaller to what we want. These are all the same techniques that we use for linear combinations. And what's really cool is you technically know how to row reduce already. You've been doing it every time you perform linear combinations. But what we're going to see is that we're just going to write it differently. So everything you know about how to do linear combination method, the elimination method from Algebra 1 to solve a system, is everything you need to row reduce for a matrix. We're just going to write it a little bit differently and show how to work that out. Here are things that you're not going to find in a textbook that are really, really important for you to keep in mind. Once we get better at how to row reduce, you won't always have to be as rigid with these rules. But these rules will work 100% of the time. So here's how we're going to do it. You must work column by column. No matter if you're an expert at this, this rule still holds. You have to work column by column, and you must work with the first column, complete that column, go to the next column, and so forth. You can't just randomly say, well, I like column number 5, so I'm going to go to column 5 and work on that one first. You're going to be doing a lot of extra work that way because you're going to have to fix it later. So you work column by column. You do not move to another column until you've gotten all the necessary zeros before you go any further. Once you've gotten your zeros, then you can find your pivots. So pivots, yes, we know they're pivotal to our answer, but it's a lot easier to take any number and reduce it down to a 1. If I have the number 3, I can multiply 3 by 1/3. I can scale, and that 3 times 1/3 becomes a 1. It's a lot easier to get a 1 than it is to get a 0. So the first thing we're going to do is get all of our zeros that we need, and then the second thing we'll do is to get our pivots by scaling. So that's really, really important for us. Now, here is the massive hint. The hint is this. If you're working in column 1 to get your zeros, you're going to use row 1 to manipulate. If you're working in column 2 to get your zeros, you're going to use row 2 to manipulate. If you're in column 5, you're going to use row 5 to manipulate. So whatever column you're in, you're going to use that equivalent row to make the manipulations. This is really, really important and very helpful in terms of what in the world we're doing. So these are the rules, and we're going to continue to refer to them over and over and over again. But we can replace, we can switch, and we can scale. So basically we can add, switch, and scale. And we're going to work column by column. We're going to get our zeros first and then get our pivots. In whatever column we're in, we're going to use that equivalent row to do the manipulation. Now, before we actually jump into seeing a matrix and how it works, what we're going to do is we're going to walk through a system. And this system we're going to use for linear combinations, the way we did in Algebra 1. And then we're going to do the exact same system using matrices and see exactly how they are the same, just different ways of writing it. So if I have this system, and I have 8x plus 6y equals 2, and then 5x plus 4y equals -1, how would we do this way back in the day? Well, in Algebra 1, what we would say is we want to pick a variable we want to eliminate. What we see is the x's are lined up nicely, the y's are lined up, the equal sign, and also the constants. So we're already ready to go in terms of combining things. Well, let's get rid of the x's. So if we get rid of the x's, that means they have to have the same number, opposite signs. What do we see? What we see is that this guy has an 8 and this x has a 5. They're not the same number, nor are they even opposite signs. So what we're going to do is we're basically going to do a switcheroo. So we're going to say, I'm going to take this 5 and I'm going to bring it up top. I'm going to move that. And I'm going to put a 5 up here. Well, I'm going to do the exact same thing. I'm going to take this 8 and I'm going to bring it down. So by doing that, I can now multiply the entire top row by 5 and the entire bottom row by 8. But that's still not going to get me exactly what I want. I still need them to be opposite signs. So if you notice, do you agree it looks like we're in the first column? Well, we are. So which row do we use to manipulate? We would use the top row. So we're going to make the top one negative. We're always going to do that. So now what we're going to do is we're going to distribute these numbers into the entire equation. So that means -5 is going to be distributed to everybody in the top row, and then 8 is going to be distributed or multiplied by everybody in the bottom row. This is what we did way back in Algebra 1. So if we distribute those numbers in, -5 times 8 gives us -40x. -5 times 6 gives us a -30y equals -5 times 2, we have a -10. What did we do? We didn't change the chemical makeup of the equation. We just made it bigger. Could we factor out a -5 and come right back to where we started? Yes, which means we haven't done anything illegal. We just made them easier for us to use. So if we multiply the entire bottom equation by 8, 8 times 5 is a positive 40x. 8 times 4, what we see is we've got a positive 32y. And 8 times -1, we see as a -8. Once again, we haven't changed the chemical makeup of that equation. He's still 5x plus 4y equals -1. All we did was just make him a little bit bigger by multiplying by an 8. The reason we wanted to do that is now we notice they not only have the same number, they have opposite signs. So now we're going to add them because that's how we can replace. We can add. So we're going to add these two equations up. -40x and a positive 40x got eliminated. It made a 0, which is what we want. Again, we're looking for our zeros. And if we add those two numbers up, we've got a -30y plus a 32y, and we see it's a plus 2y equals -10 and a -8 make a -18. Well, now we've got 2y equals -18. If we divide by 2, y equals -9. So now that we know that y equals -9, all we got to do is find what x equals. We have a choice. We can take this -9 and plug it into either of our new and improved equations or into either of the original equations. I probably wouldn't plug it into the new and improved because there's bigger numbers. But we get to decide how we want to do that. We can take this -9 and we can plug it into either the top equation or the bottom equation. It doesn't really matter. If we choose the top equation, that means we have 8x plus 6 times -9 and then equals 2. So now what are we going to do? We're going to simplify. Well, we've got 8x and then minus 54 equals 2. All right, so now let's add the 54 over and we get 8x equals 56. Divide by 8. X equals 7. Well, that means we found the solution. We found the value of 7, -9. Well, this is everything that we're going to do for matrices. I'm going to leave this up and I'm going to erase that side, and I'm going to take this exact question and we're going to put it into a matrix, and we're going to perform the same, in essence, operations. We're just going to write it a little bit differently, and we're going to see that we're going to get the same outcome in the end by just performing row operations using matrix form, which is exactly like linear combinations. Here we go. All right, same exact system. We already know what the answer is. We already know what we had to do. Let's now put this into an augmented matrix and see what we can discover. So if we put this into an augmented matrix, that means we're going to put our coefficients, 8 and 5 for the x's, 6 and 4 for the y's. We're going to put our bar for the equal sign, and then 2, -1. So what makes this a little bit different? Well, we're getting rid of the variables, and we don't have to deal with them. We can bring them back in at the end. We're just dealing with the numbers, which is what we need anyway. Well, if we're working in matrix form, we have to work column by column. So that means we are in column 1. Our ultimate goal is to get everybody in the column to be 1s and 0s. That's what we want to do. Well, what's more important? The big hint was get your 0s first, then get your 1s. So get the 0s, then the pivots. So if you notice, if we're looking for that diagonal to be a 1, that means everything above and below must be a 0. Well, that means the 5 really does need to go away, because the 8 will eventually become a pivot. It'll eventually become a 1. Again, remember, our ultimate goal is to get this. This is what we're looking for. That's what our objective is. We want to get 1s down the man diagonal, everywhere else to be 0s. So that means we eventually want to turn the 8 into a 1, but that's not important to us right now. The most important thing is to get that 0. So what are we going to do? We need to get rid of them. How do we get rid of them? Well, we can add, replace, we can switch, interchange, or we can scale. Well, what did we do over here? We added. Maybe we should do the same thing. So how'd we do it over here? Well, we got the numbers to be the same, opposite signs. Maybe we should do the exact same technique, and that's exactly what we're going to do. What we're going to say is, well, if I am in column 1, I'm going to use row 1 to manipulate. So once again, what I'm going to see is I want to keep this guy, but I want this one to go away. I'm going to switch those two numbers once again. So I'm going to say this is a 5 and this is an 8. Now, we did the exact same thing over there, but we recognized over there that we needed 1 to be positive, 1 to be negative. Well, whatever column you're in, that's the row that you're going to use predominantly to manipulate. So we're in column 1, so we're going to manipulate the most using row 1. So if we need a negative, he gets the negative. If we were in column 2 and we needed a negative, that means row 2 would get it, because that would be the column-row combination. So what do we do now? Well, we're about to manipulate, meaning we're about to distribute into everybody that we see. We're not changing the makeup of the original matrix, we're just going to make it bigger, just like we saw here. Now, every time we perform an operation, we need to put some command lines down, meaning you have to tell the reader, whoever it is looking at your work, what did you do? I don't understand. How can I follow you quickly so that I can see every manipulation you make? Now notice, we just wrote down that we're going to take and multiply -5 by the entire top row and 8 by the entire second row. Well, that's the command line we're going to write. We're going to say -5 row 1 plus 8 times row 2. Well, we're going to take -5 and multiply entirely through row 1 and 8 entirely by row 2. And we want to eventually add them, just like we did here. What do we want to do? We want this guy to go away, which is exactly what we saw there. We want him to disappear, which means we're going to say, I want us to eventually change, let's change row 2. Why row 2? Because that's the location that we need to go away. That's the elimination part that we're looking for. So we're going to multiply 2 rows and then add them together, just like we did there. This is the command line, which is what your professor or anybody looking at your work wants to see. Now, every time you manipulate the matrix, we need to say, I am manipulating, I am performing a row operation. I'm going to put the wiggle in there saying, hey, operation is about to happen. So that means I'm going to, in small little blue writing, going to write up high above those numbers. Again, when you get really good at this, you can do it all mentally in your head. So if you can multiply and add numbers quickly and easily and arithmetic is no problem for you, then you don't need to write this down. For the rest of us mere mortals, we might need to write it down because we don't want to make a silly mistake. I make silly mistakes with arithmetic all the time. So make sure we get it right by writing it down. If we have to, you can write it in pencil, you can write it really faintly, you can put it on the side so no one will ever know that you wrote down these numbers, but we just got to make it right. So I'm going to do it in small little writing in blue so you can see the manipulation. If I take this -5 and multiply by 8, I get a -40. -5 times 6, we get a -30, and -5 times 2, we get a -10. Well, we saw that over here. All right, if we take the 8 and we multiply them all the way through, 8 times 5 is a +40, 8 times 4 was a +32, and 8 times -1 gave us a -8. Well, we did exactly what this blue command line said to do. We multiplied the first row by a -5, we multiplied the second row by a +8. What do they want us to do now? Add it. Okay, I can add these little blue numbers. Who do we want to change? We want row 2 to change. Well, that means row 2 is the guy that's changing, which means the original row 1 is going to stick around. Now that's interesting. How come the original row 1 is staying and I'm not writing -40, -30, and -10? Because what would be easier to work with later? Big numbers, little numbers. So whichever row we need to replace, that's the only one that gets affected. Because I don't want to have to eventually deal with -40, -30, and -10. You could if you wanted to, but it's so much easier to kind of say, you know what, I never changed the chemical makeup over here, just made it bigger, so I don't have to keep using these big numbers. Let's go back to the original. The only one that's getting changed is row 2, because that's who I'm looking for. So let's add the little blue numbers together. -40 and +40 made the 0, just like we saw here, just like we're looking for there in terms of our matrix. -30 and a +32 gave us a 2. Well, what do we see? -10 and a -8 made a -18. What you're seeing is exactly what we see here in our line when we simplified using linear combinations. Everything is identical, just written differently. So now, we have finished, completed column 1. Notice column 1, we need to keep everybody to be 1s and 0s. What's most important? Getting your 0s, and at the very end, get your 1. So we don't need to change the 8 into a 1 just yet. We just need to get our 0s. Now what we're going to do is we're going to move to our second column. If we're in the second column, we want to manipulate using the row 2 column. So notice, it's mimicking what we want in terms of the identity. We want this 2 to stick around. We want the 6 to go away. So if we want the 6 to go away, we want him to become a 0, like we see here. Well, if we are in column 2, that means we're going to use row 2 to manipulate. So instead of using the 8 and the 0 like we see here, we're going to use the 6 and the 2 because we're now in column 2. We're going to use row 2. So what we're going to do is we're going to make a little bit of a switcheroo. We're going to switch those numbers around. Now, I'm going to do something that you probably can recognize and say, well, why is she multiplying by 6 and 2? 2 goes into 6 3 times. Why can't we just use that? We absolutely can, and we're going to see that we're going to get better and better at it. But what we're going to do is we're just going to switch those numbers. So now, we know that we're going to switch the 2, and we're going to switch the 6. Here's the question. Are they opposite signs? We just switched the numbers, but they're not opposites. So one of them has to be a negative. Which one is it going to be? Well, if you're in column 2, that means you're going to use row 2 to manipulate. So the row 2 is going to get the negative if we have to have a negative, which we do. So again, we're in column 2, so row 2 was the manipulation part. Row 2 is going to get the negative. What are we about to do? Well, we're going to write our command line. We're going to say, I want us to multiply -6 by everybody in row 2, and I want to multiply everybody in row 1 by a value of 2, and I want us to add it together. So once again, we want to do an elimination method. We want to basically eliminate the y variables a little bit. So what's happening is we're going to multiply the entire second row by a -6. We're going to multiply the entire top row by a 2, because those are the 2 manipulations we're going to see. And we want to change row 1. Why row 1 this time? Because that's the 0 that we're looking for. That's what we're trying to gain. Now notice something really cool. If you notice, the first guy tells you what column you're in. The second guy is who's getting changed. The first guy is what column you're in. The second guy goes twice because he's the one we're trying to change. That's the way all of our commands will always be to keep things organized. So we're going to perform a row operation. We're going to put the wiggle in there. Now, again, if you were really good at using arithmetic and adding and multiplying numbers, go for it. That's awesome. If not, write it down. So we're going to do exactly what it says. We're going to multiply the entire second row by a -6. Here we go. 0 times -6, well, is 0. I'm going to erase this so we can kind of write it down. So we have 0. 2 times negative 6 is a negative 12. Negative 18 times a negative 6 is 108. Now, if we multiply the entire top row, row 1, by a 2, let's see what happens. 8 times 2, we get 16. 6 times 2, we have 12. And 2 times 2, we get 4. Notice that these are the little orange numbers. That's what we're going to be adding. If we can do this in our head, great. Otherwise, just write it down. So we're going to manipulate. Which row are we looking to change? We want to change row 1, which means row 2 isn't changing. We were happy with row 2. We'd already affected him on the previous example. So we're going to keep 0, 2, and negative 18. Why? I don't really want to keep 108 if I don't have to. I mean, it's up to you. But I'd rather keep the smaller numbers. Again, by just multiplying an entire row by a number, you're not changing that equation. You're just making it either bigger or smaller. So use the numbers that are easier. Only affect one thing at a time. So now, let's add up the little orange numbers exactly like we see here. 16 plus 0 makes 16. Wait a minute, my 8, he changed. Who cares? If I take an 8 and I multiply it by 1/8, we get 1. If I take 16 and multiply it by 1 over 16, we still get a 1. It doesn't really matter that we haven't changed them yet, and that's why we don't change our pivots to the last minute. So 12 and negative 12 make 0, which is exactly what we were looking for. And then 4 plus 108 makes 112. All right, so now we have completed the hardest part of row reduction. What we see is that we've got the zeros everywhere we're supposed to have a 0. We've got 0 in the lower triangle, and we've got 0 in the upper triangle, just like the identity matrix that we were looking for. Perfect. What's the only thing left for us to do? Scale. We want to get these numbers along this diagonal to become 1s. So how do we get a 16 to become a 1? We multiply by its inverse, 1 over 16. How do we get a 2 to become a 1? Multiply by 1/2. So that's the operation we're going to perform. And we're going to write that command line. We're going to say, I want us to multiply by 1 over 16 times row 1, and it's going to change row 1 to make it easier. We're then going to say 1/2 row 2 is going to change row 2. Again, we're just telling the reader what you're about to do. And then if we do it, we're going to manipulate it one more time. We're going to say, okay, I'm about to perform an operation. There's my wiggle. And we're going to change both of those rows. We're going to multiply the entire top row by 1 over 16. So if we say 1 over 16, and we distribute him in, 16 times 1 over 16 becomes a 1. 0 times 1 over 16 stays 0. And then 112 divided by 16, well, look at that. You get 7. So 112 divided by 16, we get a 7 value. Perfect. So now, let's take 1/2 and multiply it by the entire second row. So we have 1/2, and we're going to distribute, in essence, scale him in. 0 times 1/2, 0. 2 times 1/2, 1. Perfect. I've got my pivots. I've got the 1s down the main diagonal, 0s everywhere else, top and bottom. And then negative 18 divided by 2, or times 1/2, we get a negative 9. Well, would you look at that? This guy looks just like that guy. It's just written a little bit differently. Notice we have x equals 7, y equals negative 9. If we remember, this is the x and y columns, and we know this is the equals, well, we're ready to go. That means x plus 0y equals 7, and 0x plus y equals negative 9. Well, x equals 7, y equals negative 9, just like we saw over there. So, linear combinations is the exact same way that we perform row operations. We've now proven it. What's interesting is that we were able to do the same manipulations, write some command lines, and get our overall objective. We took our time to make sure that we could guarantee that we're never going to get this wrong. Now, What did we perform? We performed RREF, reduced row echelon form, Gauss-Jordan elimination, because we got ones down the main diagonal, our pivots, zeros everywhere else. Did we have to? No, we could have actually stopped right here, and we could have actually done back substitution like we did on the previous question where we saw for linear combinations, and we would have gotten the same answer. But we're just walking ourselves through techniques. What we're going to do next is we're going to look at an example of how to just do REF, row echelon form. And then for the next examples, which we're going to see, we're going to continue to perform our REF. Out of the two operations, our REF is the more powerful and the more useful. REF is very effective if you only need to determine certain things, but again, it would still require back substitution. So let's look at how to do REF, and then for the next bunch of examples, we'll do our REF, which is the more powerful. Here we go. All right, so for this example, it says use REF, row echelon form or Gauss elimination to solve the system. So what we see here is we're given this basic system, two equations, two unknowns, and what we're going to do is we're going to put it into an augmented matrix. In order to perform REF or RREF, you must be using an augmented matrix. So here we go. We're going to put it into an augmented matrix. We're going to keep our columns nicely organized and pull out the coefficients. So we say we've got 1 and -1 for the x1 column. We have -2 and 3 for the x2 column. We're going to put our bar in for the equal sign, and then -1 and 3. So we've now successfully created that augmented matrix. Now, what is one of the most common mistakes is we transcribe wrong. I've done it myself. And so how important is it that to make sure we copy correctly to get our matrix? Because if we copy it wrong, then everything we do after that's going to be wrong. So take your time, double check yourself to make sure that you've transcribed it correctly. I've made the same mistake myself. So what we've done is we've now written the augmented matrix, and now we've got to think, what is the overall goal that we're looking for? If we know we're looking for REF, that means we are looking for ones down the main diagonal, zeros below all of the ones, but we don't really care what happens in the upper triangle. So that means we only really need to get 1 0 and scale on down. That's not so bad, it just means extra back substitution to get our answer. So what do we want to do? Well, we want to get this guy, -1, to become a 0. Well, let's go ahead and put that in there so we can say, hey, I want him to become a 0. So I'm going to actually put it in there and say that's what I'm really wanting to get. Now, what column are we in? We are in column 1, which means we're going to use row 1 to manipulate. So we're going to switch those numbers. Well, they happen to be the same, 1 and 1. Do we need a negative? Well, one's positive and one's negative already, so we don't need to put a negative in there. All we got to do is switch those values. So what do we want to do? We want to switch the numbers and then add them together using our addition property, our replacing property. We want to replace this guy with a 0. So we're going to write our command line. Our command line says, hey, I want to multiply the entire top row by 1. So we'll say 1 row 1, or just row 1, plus 1 row 2. So I want to add these two things together just like I would see in linear combinations. If we just put our big bar and put a big plus there and we could add them up, that's what I want to do. Well, who wants to be replaced? Who are we trying to manipulate? We want the row 2 to go away. We want this guy to be replaced, so we say row 2. Again, we got to say whoever comes first is the column you're in. Row 1 corresponds to the column that is column 1. Row 2 better come twice because that's who we're going to be affecting. So if we do that, we're about to manipulate, so we say wiggle. So equivalent matrix is about to come up. We're going to only replace row 2. We're going to keep row 1 exactly the way it is. So we're going to rewrite row 1 so we don't mess it up and don't get anything weird. And what we're going to do is we're going to now perform the operations they want us to. Well, this one's pretty nice, but just because I want to make sure that we see that we're doing something, I'm going to still write it in the little blue color. So it says multiply the entire top row by 1. So 1 times 1 is 1, 1 times -2 is -2, -1 times 1 is a -1. I've successfully multiplied. What about the second row? We are going to multiply the entire second row by a +1. Okay, so -1 times 1 is a -1, 3 times 1 is 3, and then 1 times 3 is 3. I've done exactly what it says. Now all we got to do is add them together. Okay, 1 plus -1 makes 0. Perfect, I got exactly what I wanted. So now, -2 plus 3, what we see is 1. All right, and -1 plus 3, we get a value of 2. So we have now completed column 1. We have gotten the 0 that we were looking for. And if you notice, we are actually perfect in terms of REF manipulation. We have exactly what we're looking for. We have our pivots down the main diagonal, and we didn't even have to scale. And we've got our 0 in the lower triangle, and it doesn't really matter what that number is above. What we now see is that we can pull this back out into a system. This is called general form. So general form now says rewrite what you've got. Again, this is x1, x2, there's the equals, and again, these are the constants. So we see that we've got x1 minus 2x2 equals -1. But what we see here is that the second equation has gotten better. We now have just x2 equals 2. We have performed our general form operation by using REF. Well, what are we going to do now? Unfortunately, since we didn't do our REF, we still have to find out what x1 is by back substituting. So now, back substitute. We're going to take this value and we're going to plug it in. So what we have is x sub 1 minus 2 times 2 equals -1. So x sub 1 minus 4 equals -1. X sub 1 equals 3. If I add the 4 over, 4 plus -1 equals 3. Now what I've got is x sub 1 equals 3, x sub 2 equals 2, or it's the ordered pair 3, 2. So REF is pretty straightforward. All we're doing is getting our zeros in the lower triangle. And then we would get our pivots if we need to, which what we saw was a pretty straightforward question. But the irritating thing at the end is that you still have to back substitute. And no one wants to do that, especially if you've got a bigger matrix. This one wasn't hard, but imagine if you had 5 equations and you had to back substitute 5 times. Ooh, that'd be really frustrating. So REF is definitely effective, but it's not as powerful as our REF. And here's something that's very, very important for you to know. REF, there are an infinite number of possibilities on how to solve using REF. Because what was stopping me from saying, you know, I don't like the way it's written? I could have said, well, why did that top equation come first and the second equation come second? What happens if we then said, okay, if we had this, 1, -1, and then -2, 3, and then -1, 3, well, how come that row's on top and that row's on the bottom? Why? Well, it's because the textbook or the professor or I chose it that way. But it doesn't have to stay that way. I want to switch them because that's what I want to do. So we could switch. I want to take the second row and move it to the top row. I can say I want row 1 to switch with row 2. Notice it's the double arrow that we're seeing here. I want them to switch. Why not? Because we can. There's nothing saying that we could put one before the other. So we would then say, well, this would be -1, 3, and 3, and then 1, -2, and -1. I can switch, I can interchange any way I want to. So what's really important is there are an infinite number of ways to solve a system using REF. So that means I can get one value and then you can get another matrix in the end. So this matrix right here, I could get, but I can get something totally different if I wanted to, if I had changed the way this was written. I can totally get different possibilities. Well, why did I multiply both of them by 1? I want to multiply both of top and bottom, row 1, row 2 by 17, because I like the number 17. So we can have an infinite different possibilities for REF. What's so cool though, that every single person in the world will get the same exact REF in the end, no matter what we do to get there. So I could take 7 steps to get to the final outcome, and you can take 2. We will still arrive at the same answer, and all of our answers will be exactly the same if we're going to use REF. Now, if we use REF, just row echelon form, we can have an infinite number of possibilities. But every single person will get the same exact REF in the end. I hope you've enjoyed the lesson so far on row reduction techniques. For an additional question where we look at how to row reduce a 4x3 matrix, check out calcworkshop.com.